إذا كررت هذه العملية بعد أشهر
Assalamu alaikum. Good afternoon. Unfortunately, we're having a little bit of technical difficulties. So what we're going to do, I was going to start with my presentation, and then I was going to share with you a video that talks about the legacy of the technology. The title of my presentation is Cognitive Intelligence. Cognitive intelligence is a higher form of artificial intelligence. Before I start, maybe just a quick survey. Anybody in the field of AI or artificial intelligence? Mumtaz?
I just used it before. I don't study.
Okay. Mumtaz. Is it mainly machine learning, deep learning? Is that? Okay. Okay.
I didn't particularly study AI or machine learning, but I used some tools.
Okay.
Like vision AI services.
Okay. So I'm going to talk to you about what we call conventional AI and this cognitive intelligence. But maybe before I do that, since we have to run it on two separate PCs, if you can indulge me, I want to show you a little video that talks about our technology and where our technology came from. The video is, the title of the video is 7 Minutes of Terror. And it's about landing the Curiosity rover on the surface of Mars. Any of you familiar with the Curiosity rover? Okay. So this is a big Land Rover that we actually landed on Mars. And I can tell you, this is a difficult job. So I wanted to share with you what it took, the kind of capabilities and technologies to land a platform that is 12 feet by 6 feet, going from 13,000 miles per hour to land it gently on the surface of Mars. I think with that,
still looks great. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars stands away. So when we first get word that we touch the top of the atmosphere, the vehicle has been alive. And then, on the surface, for at least 7 minutes.
Entry, descent, landing, also known as EDL, we refer to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help program. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag out each year. It heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constraint space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with. Otherwise, it would destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time for the rest of the landing sequence to work.
This big, huge parachute that we've got, it only slows down to about 200 miles an hour. That's not slow enough to land. So we have no choice, but we've got to cut it off and come down with rockets. Once we turn those rocket motors on, we don't do something. We're just going to smack right back into the parachute. So the first thing we do is make this really rapid that we're going to fly off to the sun.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land, and we're going straight down to the bottom of the crater, right beside a 6-kilometer-hour mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms, and it could damage instruments. So the way we solved that problem is by using the sky crane.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit on its wheels on the surface.
As the rover touches down and is now on the ground, in the same state, it's in a collision course with the rover. We must cut the driver immediately and fly to the same stage to a safe distance from the rover.
Do you agree? I mean, this is a tough problem. So this is all done autonomously. So during 7 minutes, we have absolutely no contact. If you want to switch to the other one, absolutely no contact with the spacecraft. This is why we call it the 7 minutes of terror. So we're building intelligence system, cognitive systems, AI systems to manage that entire sequence. Any misstep and the spacecraft is lost. So this is what we call cognitive intelligence. Yeah, you're on the right slide. So go up. I thought I'll give you a little background about the company. The company called Beyond Limits. We are a spin-off from NASA, وكالة الفضاء الأمريكية. And just in terms of a quick background, I know I talked to one gentleman here. So are you familiar with Caltech? California Institute of Technology. That's Caltech was established in 1891 by 4 individuals: Arthur Noyce, George Hale, Albert Einstein, and Robert Milken. They wanted to create the best world-class facility in Pasadena for physics research. And they created one in Pasadena. Their curiosity led them to basically launch rockets in the 30s. And they did that, and they burned down the university in 1936. So the fire department came back and said, you can't do that anymore. So they kicked him out to a very outside of the city, and they built this world-class facility called NASA's Jet Propulsion Laboratory. So NASA is 10 centers. 9 of them focus on what we call the manned space program, and the Jet Propulsion Laboratory only focuses on the unmanned space program. Just a little bit of history. JPL actually was created 22 years before NASA was created. In 1957, the Soviet Union, younger generation, you don't remember the Soviet Union, but they launched a satellite it was the first satellite in space called Sputnik 1. President Eisenhower, who was the president at the time, wasn't happy about that. So he went to his generals and admirals, and they said, you know what? Go talk to a bunch of crazy scientists in California, and I think they'll do the job. 4 months later, after Sputnik 1 was launched, Caltech JPL put Explorer 1 into space. Explorer 1 is a Caltech satellite. So that started the whole mandate for JPL to explore our solar system. So we've been to Venus, we've been to Mercury, we've been to Mars, we've been to Jupiter, we've been to Plato, and I'm happy and proud to say we have the only man-made object outside of our solar system. It's 2 billion miles away, and that's the Voyager 2. So sometimes when people talk about IoT, we say, yeah, we have an IoT system. It's about 2 billion miles away. So the company was created to take the technologies and to take them into the commercial arena. And what we're doing right now is we're applying those technologies to energy sector, healthcare, financial services, transportations, and logistics. So I wanted to talk about AI. So AI, or artificial intelligence, it was coined artificial intelligence back in 1956. So AI has been around for a long time. But AI did not become popular until the last, I would say, 8 years. The reason for that is because we really didn't have lots of data. Now with social media and with digitization, we have lots and lots of information. That's why machine learning and deep learning became very popular. The other aspect that helped basically promote AI was microprocessing capability became very less expensive. So you heard Dr. Sennett this morning. I mean, we're driving the cost of microprocessor and silicon. I mean, it's so cheap right now. We can do a lot of processing capability. So the abundance of data and the low cost of computing power led to just explosion of AI. Unfortunately, it's still what we call a narrow AI. Are you familiar with narrow AI versus strong AI? So narrow AI talk about AI doing a specific task. And guess what? It can do a specific task better than humans. So I want to give you examples. Any radiologists, any doctors? فين الدكاترة هون? Do you know that AI system can read a صورة أشعة better than any doctors? We achieved that level of performance. In fact, now in pathology, we're moving in that direction. AI can basically detect cells better than doctors. Now, don't misunderstand me. I'm not saying that AI is better than humans. All what I'm saying, for the specific task, for that narrow task, machine vision, for example, AI can do a better job than humans. So that's where the focus so far in terms of where AI is. Now the problem, if I can take that system that can read Surat al-Ash'a or the pathology report and ask it to diagnose something else, it will fail. Because the data has been only trained to do a specific task. This is the difference between AI and the human mind. إحنا كhumans, we have what we call general intelligence, not narrow intelligence. So although narrow AI can beat us in a specific field, so far it hasn't been able to catch up with us in terms of a general intelligence. So what are some of the problems? And again, I want to apologize in advance for all of you who are machine learning, deep learning. I don't mean to bash machine learning or deep learning. I just wanted to explain to you the difference between what we call conventional AI and cognitive intelligence, which is a level above machine learning or deep learning. Machine learning, deep learning is phenomenal capability. It is so accurate. I think somebody this morning asked the question about, using social media, and it recognizes your habits and will basically recommend certain things. It is amazing what they can do now with the data and machine learning and deep learning. The other important thing that we're doing right now is most of the data that exists today, that we handle today, is what we call unstructured data. So it's not clean data, it's not formatted data. Merrill Lynch, in 1998, they estimated that 80% of all data that exists is unstructured. This was back in 1988. This is before social media. This is before the revolution of mobiles. Imagine now, that number is significantly higher. So one thing about machine learning and deep learning is you cannot take unstructured data and just dump it into the AI system. You have to go and clean it. This young man here was asking me about natural language understanding. This is the tool that's going to help us basically clean a lot of those unstructured data and make them in a format that AI system can handle. So what is cognitive system is fundamentally different? Because what we did here is we try to approach it the same way the human brain thinks. So there's a lot of research in what we call bio-inspired artificial intelligence. We can look at the human brain and figure out how the human brain functions, okay? And we can basically emulate and simulate a lot of those functions. And that's part of what cognitive system is doing. The other thing is, on machine learning and deep learning, you're basically taking you're training based on experience. And what I mean by that, we're giving the system a set of data. We're telling the system to learn from that set of data. Now, if I go back and I say, well, I want to change one parameter, guess what? You have to go back and retrain the system. We as humans, we don't think that way. If you give me a problem and you tell me, here are the tools for you to solve the problem. If one of the tools is missing, I'm not going to stop there. I'm going to think outside the box. I'm going to think about ways to solve this problem. That's the difference between cognitive intelligence, human-like reasoning, and what we call machine learning and deep learning. Again, machine learning and deep learning is phenomenal, but you have to design it. You have to basically give it a set of rules. If those rules change, then it's not going to work. You have to retrain the data. So the example I showed you about landing Curiosity on the surface of Mars, imagine now, I mean, it takes us 6 months for the spacecraft to get to Mars. The signal takes about 2 hours. Imagine now if one of the rules is broken, or if I have a different set of rules. It doesn't work that way. So that's why we had to go beyond conventional AI and look at cognitive intelligence, look at human-like reasoning, how we can emulate the human brain, and how we can focus on that. If you look at us as humans, what we do, أنت لما تتخرج من التوجيه and you graduate and you go to college, whether you're studying medicine, هندسة, whatever the case might be, when you go to the university, your basic knowledge is limited. But after you graduate, now you've learned a lot from textbook, from lectures, and that's what we're trying to do. Once you graduate as a doctor, then you go into what we call an internship program, which means you work in the hospitals, you work with patients. That's where experience comes. So what we're trying to do, and the way we solve the problem for NASA, is we combine both conventional AI, machine learning, and deep learning, where you have lots and lots of data, and basically teaching the systems based on education. That combination of knowledge and information is very relevant to our systems. Anyway, I'd like this to be informal. So if you have any questions or comments, please don't hesitate to ask. I talked a little bit about this. So our system, the system you saw for the Curiosity Mars rover, it's educated. It's the same as the الطالب اللي تخرج من التوجيهي ورايح الجامعة. We educate it. We put it through a university training, and we teach it a lot of things. We teach it physics models, because again, when you're in space, you're dealing with a dynamic environment. You're dealing with missing and misleading data. So you're gonna go back to your textbook. You're gonna go back to the training, the knowledge you got, to work on things like that. And then you're gonna use the data training to handle things that we are very aware of. So this is what we call the pyramids of machine intelligence. So once upon a time, we all dealt with what we call data analytics. That was a very popular field. So there probably are hundreds of thousands, maybe millions of applications out there. The problem was we all of a sudden were trying to get data, and we're trying to figure out what to do with that data and manage that data and clean that data. That led to a field we call data science. So in data science, you have the data, but you need to extract the right information out of that data. And companies like IBM with IBM Watson and DeepMind excelled in that. So this is, you may hear it as data warehousing, for example. The problem there is, okay, you got the right information, but I need that information to mean something to me. Telling me that, if you're looking at an X-ray, telling me that this is a red zone versus a black zone is really not interesting to me. I understand if there's something that a doctor needs to pay attention to or not. That's what we call actionable intelligence. And that's where we've been focusing on cognitive reasoning and cognitive OS. So what we do is we take the information extracted by machine learning and deep learning, the label data, and then we basically have the cognitive reasoner do actionable intelligence. That spacecraft you saw, it was basically making decisions on its own. It was extracting the data, and based on the environment it was doing, it was really doing what we call human-like reasoning. That's at a different level of thinking. I talked about this. Let me tell you, it's impossible to replicate the human brain. SubhanAllah, it's impossible. We're never gonna get there. Even if you get close to it, I mean, the power here, you're looking at a power that's powering a mobile phone. For us to allow us to do a single algorithm, by the way, the brain is a single algorithm. To allow us to build a single algorithm, I probably need Natihat Sahab in terms of air conditioning and power. We're never going to get there. It's just not feasible. But what we can do is we can look at the brain, and we can look at the different sections in the brain, and we can basically build bio-inspired algorithms. We're never going to get there, but Afwan? Oh, I apologize. So here we can actually take certain machine learning and deep learning algorithms, and we can start building a comprehensive a system of systems, if you will. That's the only way we're going to get as close to human-like reasoning and human-like intelligence. And that's the research we've been doing at Caltech for decades. And actually, it's been producing some phenomenal and amazing results. If you think about it, if you look at a human, look at the human eye, for example. The human eye is an amazing device. The human eye is not intelligent, but it does a lot for the human brain. You know, when you look at something, the human eye actually, believe it or not, it filters a lot of the information out for the brain. It only sends the right information to the brain. And that's what we're trying to replicate, is how we can take perception, take data from machine learning and all kind of data and process it to an executive reasoner, which is the equivalent to the human brain, so we and leverage also knowledge to basically come up with actionable intelligence. That's the goal. Human-like reasoning. We're never going to get to the level of intelligence of a human brain, but actually, by focusing on certain tasks, we may actually outperform humans in certain tasks. This is for full disclosure, this is a McKinsey slide. And for those of you who are interested in AI, what McKinsey talked about is most AI systems today are software. There are companies out there that actually build machine learning tools. You will be amazed, like for example in California, we got some super smart kids that building their own machine learning algorithms. And some of them are actually better than some of the professional packages, out there. But according to McKinsey, in an era where we're moving into an IoT, we really need to push the intelligence at the hardware level. I cannot process intelligence in the cloud. If I need to do something, for example, an oil field, and I need to process AI at the oil field, I don't have the time to basically take it to the cloud and basically have the cloud come back with the results. Take autonomous driving, for example. Autonomous driving will never materialize, will never happen if you're basically going to run it based on the cloud. It doesn't happen. The Google Waymo car, I don't know if you're familiar with that. This is the Google autonomous car. In the trunk of that car, there is 4 Xeons processors. That's the data center. In the Google car, there is a data center in the truck that is processing all that information. If we eventually want to make autonomous driving a reality, not only the cars need to basically have AI, traffic lights, even the streets, they need to talk to each other. Vehicles need to talk to each other. You need to talk to the traffic light. That's all going to require intelligence at the sensor level, at the edge. This is what we call inferencing at the edge. But quickly to the McKinsey slide, McKinsey thinks that almost 40 to 50% of the monetization and the value is going to be driven from what they call solution and use case scenarios, and also from hardware solution. So building AI chips. Dr. Sanad Lyom talked about building these advanced 3D memory chips. We're talking here about building actually AI on a chip itself. According to McKinsey, the monetization also 40 to 50% is going to come from the hardware side itself. If you are a company and there's a cottage industry out there, all what they do is they train data. If you basically training data, you want to re-examine your business model. You're going to be out of business. It's just not gonna work. Or if you're only selling machine learning tools, you need to also re-examine that business model. So what we're doing and what we did, we're leveraging the Curiosity rover. We're actually building, have you heard of companies like NVIDIA? I'm just a quick, NVIDIA? Okay. So NVIDIA, phenomenal company. They took machine learning and deep learning. They optimized it. Interestingly enough, they started with gamers. I mean, that was really their business. But they optimized the machine learning, deep learning, and they built an empire. 10,000 employees, okay? They're reaching now a maximum because they build a 7 nanometer chip, and they're reaching just the limits. In fact, there are a lot of companies right now trying to be an NVIDIA, me too. What we're trying to do is to build the first symbolic AI chip to take that information to do the cognitive intelligence I spoke about earlier. And that combination is going to basically give us human-like reasoning at the edge. Just want to show you an example. So this is the black line. So in an oil field, when they're looking to look for oil reservoirs, the way they do it is they basically send this drilling device. It's tethered, it's connected to the oil well, okay? Now what happens is when you run into a fault, okay, you need to adjust. But they cannot adjust because it's a noisy environment. It just does not work. So what they do is they have a wireless device that sends the data based on mud and sand at like 16 kilobits. I mean, it's so slow. By the time they get that information, you notice that the drilling apparatus just missed the reservoir by a significant amount. What we're trying to do is to build an AI on the drilling device itself here. So where once it senses that there is a fault, it will adjust without calling mothership or command and control to basically go into the reservoir itself. This, by the way, ladies and gentlemen, just missing this, going from this point to this point, we're talking billions of dollars because you missed that much of the reservoir. So this is one example where you need both the machine learning, deep learning, embedded intelligence with the symbolic side. This is a project we're doing for one of the largest oil and gas companies. This is another project we're working with Caltech, California Institute of Technology. This is what we call an autonomous flying ambulance. So this is about 8 feet long, less than 3 meters. أقل من 3 أمتار. The range is 20 to 30 miles, and it can fly at about 75 miles an hour. Autonomous. So ما بعرف إذا سمعتوا, like I think it was about a month ago, كان في حرائق في اليونان, and tragically 77 ضحية ماتوا because they could not get to them in time. This vehicle would have helped. You need human beings. So where you need to go into places where you cannot send human beings, that's where you need to have AI. And we're gonna basically fly this prototype in 3 months in Pasadena. I'm actually excited about this, not just because of the first responders application, but this is maybe 10, 20 years from now. I think you're gonna see personal transportation. We're gonna basically move into that, in that direction. I think, this is Mars, by the way. I have a soft spot for Mars. But I'll pause to see if I have any questions or comments. Please. So, very good question. So if you take me, for example, if you give me a large number to multiply, I'll eventually gonna multiply it, but it's gonna take me a while to do it. Whereas if I have a calculator, I can do it quickly. So a cognitive model will take machine learning and deep learning and process all the numeric data, because that's the best way to do it, okay? Then we put a symbolic layer on top of that. That's the knowledge base I talked about. That's the education. So we apply on top of that physics models, you know. So the combination of the machine learning, what we call the numeric side, with the knowledge base, based on education, the symbolic side, that's the approach we take to the market. So I want to give you one example. I mentioned oil and gas, okay? So in oil and gas, we're working with a large oil and gas company. This company, they deal with offshore oil wells, I mean, in the Gulf of Mexico. And one big problem when they dig for oil is sand. If sand gets into the reservoir, you may lose 40% capacity. Again, hundreds of billions of dollars. If it gets into the device, it's going to damage the device. If it gets into the tanker that's basically carrying the oil, it's going to damage that. So they developed a expertise. They built a small team, and there's one scientist who's developed expertise over decades. And he just, based on his experience, they would send him to Trinidad, to Egypt, Gulf of Mexico, and based on seismic data, acoustic data, observation from the field, he would come up with a model. This guy is 65 years old. He's contemplating retirement. According to the company, based on his work, they were extracting an additional 50,000 barrels of oil again. I mean, this is a contribution of $1 billion. So obviously the company was concerned about his retirement. So I went and talked to him. I said, can you give us the data? Give me the data that you deal with so we can build a machine learning and deep learning model. He gave me 450 pages of email correspondence, PDF documents. That was the level of the data he has. I mean, imagine, just emails. In fact, it was also unstructured. It was not even structured data. You cannot solve that problem with machine learning, deep learning. So what we did is we built a symbolic model, okay? We educated the AI system based on his knowledge. We sat down, we talked about the physics model, what you look at, what kind of parameters, and we started doing that. And then with time, we started to build basically a machine learning, deep learning model, because we're getting data from the field. That approach, that combination of the numeric side and the symbolic side, because sometimes you're not going to have the data, or the data is going to be corrupt. It is very, very powerful. Please.
I have a couple of questions. First, what kind of, like, if we're talking about deep learning, we're talking about like Google, they offer us a TensorFlow.
Yep.
What are the languages or the tools that we can use to build cognitive?
I am glad you asked that question. That is a great question. Remember my pyramids of machine intelligence? Actually, we're agnostic to whatever machine learning, deep learning tools you use. I can use TensorFlow, I can use Watson, it doesn't really matter. Okay, I was told I got 5 minutes. So we're agnostic to whatever machine learning algorithms that goes into the cognitive. All what I need is labeled data. Just give me the output from your machine learning algorithm.
You just mentioned that there's a difference between the cognitive and the deep learning. But in deep learning, there's reinforcement.
Yes.
Is there a difference between the reinforcement from the cognitive?
Reinforcement,
You don't have to have the
reinforcement,
supervised, unsupervised, and
I mean, let's take, for example, the AlphaGo. AlphaGo was based on reinforcement, and it's a phenomenal advancement in, you know, but you're still talking about certain, I mean, when you went from, for example, when Deep Blue beat the chess game, that was an accomplishment in itself. They built a $100 million machine. You knew all the moves that the chess player did. AlphaGo I was told it's orders of magnitude more moves than that, okay? Reinforcement is basically having the system play against itself, so it will learn what moves it's going to do, and it will learn on the fly. That's what you called unsupervised learning, okay? It still will not do actionable intelligence because you're still working on a predefined set of rules. But it's impressive. I mean, it's impressive that it learns from actually beating itself. It learns from the vulnerability of playing with itself. But it's still, you have although it's many iteration, you still have a constraint system. It doesn't, if you have a missing rule, it doesn't function there. But that doesn't mean it's not negative. I think it's a phenomenal capability, okay? Just get that output and basically do the actionable intelligence or the symbolic side. I just think the combination of both is very powerful. Sometimes you can solve it only with machine learning, deep learning, but that combination is very powerful.
I have a question.
Yeah.
They asked about NVIDIA. You say that they are building processors or GPUs that have 7 nanometers transistors, which is very small.
Yep.
And they are almost approaching the limits. After that,
Say that again.
you said that
Yeah, the nanometer. After that.
we are approaching the limits for the
Yes.
physical limits for the size of the transistor that we can make. So there are some quantum like quantum behaviors will appear to us at this small scales. What do you think in the future we can build instead of this? What kind of materials that we can use instead of silicon, since we will have this kind of problems?
Well, they're reaching the limitation. By the way, it's not just NVIDIA, Intel, and the other chip manufacturers. It's Moore's law. I mean, you just can't squeeze more. What we're finding and what we're seeing is actually different companies coming with a completely different architecture. To kind of handle the real estate. So where the competition I see for NVIDIA is a completely different architecture, different different approach to solving the problem. If I was a betting man, actually, I would short NVIDIA stock. I see some phenomenal capabilities out there, and they're going to get a run for their money. 2 minutes. I'm sorry. Okay, 2 minutes. Just 2 questions. Please allow me. Yeah.
We ever reach in super intelligence?
We reach.
Super intelligence.
What do you mean by that?
I mean, a robot.
Yeah.
A copy from you.
Right.
Same copy. So he can make ideas. He can make everything.
Yeah.
That's possible.
Yes. So I think we're making significant advancements in terms of teaching robots. And again, as I mentioned to you, even with narrow AI, we can actually beat narrow AI can beat humans. Now, if you can basically add if you take a Marvin Minsky approach, which basically build assistive systems, we can create a system that is you can make the argument is general intelligence, not quite, but but close to it. Other people, and I think from the previous lecture, we're talking about they're not going to have the emotional intelligence as human, obviously, but it is impressive. It's going to happen, maybe not in my lifetime, but your lifetime. Yeah. Yep. Yep. That's right. Right. A great question. In fact, right now, we're seeing a renaissance in cybersecurity. The companies that are making a big difference in cybersecurity are the companies that are taking an AI approach to it. There is a company I'm very actually a fan of called Trace. It's a Cambridge out of the UK. But just to give you an example, they build AI machines. So it's a black box. You put it in your company, and it learns very quickly certain behaviors. They actually put it into a Las Vegas casino, and it was able to detect a threat coming from a wireless device out of a fish tank. I mean, nobody paid attention to this wireless device that was doing very silly things, but yet, you know, the threat came from that wireless device inside the fish tank. So I'm very high on AI-based cybersecurities, and you're going to see, you know, I think they're gonna succeed. I guess I was sold. I'm done. Thank you very much. You know, I really appreciate it.